This next section of the course is a major one in BC Calculus. We're ultimately going to get into this idea of series and specifically what's known as a power series, okay? And a power series is what many mathematicians will tell you is one of the most powerful tools in all of math. It's basically the idea is that we can take any kind of function, any kind of differentiable function, and turn it into a polynomial. And if you think about that, polynomials are really easy to work with, right? Our rules for differentiation, our rules for anti-differentiation, quite simple when you consider that with the rules for exponential functions or trigonometric functions or logarithmic functions or inverse trigonometric functions. They can get rather complicated. So why not make things easier? So we want to get into this idea of power series. But before we get into power series, we need to talk more about infinite series and series in general. And series is basically when you're adding up the terms of a sequence. So that's where we really need to begin, which is this idea of a sequence. And you've actually talked about sequences already. They've been introduced to you in previous math courses. And a sequence, as we know, is just a list of numbers that's written in some kind of explicit order. All right, it's just a list of numbers. Okay, so the notation for it, we've got braces or curly braces, if you will, around the sequence itself. So a sub n, that's our general term, which we'll get to more in a second. And then it's just equal to, okay, we got our first term, our second term, our third term, so a sub 1, a sub 2, a sub 3, all the way up to the nth term, and we continue onward from there. Okay, but the general term, that's the one that gives us our guidance. And it quite often is presented as a formula, but it doesn't have to be presented as a formula. We can also think of a sequence as a function, okay? And we know that functions have domain and range. Well, the domain of the function that was representing the same thing as a sequence would just be all positive integers. In other words, the first, second, third, fourth, the positive integers are the domain. The range is the output when we actually plug in 1 or 2 or 3 or 4 into this formula. Right? So we get, and that actually connects with the graphing calculator as well. We'll get into that as well. As far as sequences are concerned, the two most common ones, the ones that you've probably talked about already in math class, are arithmetic sequences and geometric sequences. So an arithmetic sequence is one in which there's a common difference between the consecutive terms. Okay, so if we look at this, here's an example of an arithmetic sequence. All right, 2, 5, 8, 11, and 14, so on and so forth. We're always adding 3 to get to the next term, or the previous term is 3 less than the current term, if you want to look at it that way. All right, so an arithmetic sequence quite often is written, the general form of an arithmetic sequence is the first term plus the, whatever term we're interested in times the minus 1 times the common difference. All right, that's our formula for an arithmetic sequence. You've probably seen that before. And it means that we can have a sequence which is increasing. It could be one where the terms are decreasing as well. 19, 12, 5, negative 2, we're dropping by 7. So this common difference right here, it could be a positive number, like one that would lead to that top sequence, or it could be a negative number, which leads to one like that bottom sequence. In an arithmetic sequence, again, it has that common difference. And if an arithmetic sequence has a common difference, well, then the geometric sequence has a common ratio between the consecutive terms. In other words, we're always going to multiply, or divide, if you will, by the same number to get to the next term. All right, so common example, 2, 4, 8, 16. We are doubling. What would the next term be? Yeah, it'd be 32, okay? Another possibility, instead of multiplying by 2, what if we were to always divide by 3, or technically multiply by a third? All right, 27, 9, 3, 1, a third, a ninth. Those are geometric sequences, all right? And if we were to put a general term for those, a sub n is equal, again, to the first term times a common ratio to the n minus 1 power, all right? So the common ratio here would be 2, because we're multiplying by 2. And the common ratio here would be a third. And again, that common ratio, positive, could be negative. That's what's driving our next term in our sequence. But ultimately, it's just a list of numbers in an explicit order. So that's the idea behind a sequence. In the next video, we'll do a quick example of finding some terms of the sequence and see how that leads us to our ultimate goal of the power series.